third out of 8 is the whole concept of if you're going to use HDI, once you use one laser drilled microvia, you're paying for the whole kit and caboodle. So the worst thing you can do is have a design that has 270 laser drilled holes, because you could have put in 20,000 laser drilled holes for the same price, because the laser drills about 600 vias a second. So the difference between 200 and 20,000 is the number of seconds. Once you have one microvia, you incur a step charge. And then, unlike drilled holes, you could do 200,000, same price as 20. Because at 600 a second, they go really fast. The only problem is that you don't, in your mind, you've been thinking, a mechanical, we want to minimize the number of holes. That's true for mechanical drilling. For laser drilling, don't worry minimizing. They're so cheap and they're so fast. If you want to use 10 times as many, use 10 times as many. They're very small. They're not going to cost you anything. So that's why you have to unlearn multi-layer techniques, because now you're over here in a realm called HDI, and the rules are different. But nobody ever told you that the rules are different, and the fabrication is different. And so this one is elimination of big holes. And so what I mean is, get rid of that big guy and replace him with the little one. That's a priority in concept. And the problem is that, in a multi-layer, you only have the big holes. So it's difficult to think, well, how do I replace the big one with the little one? It's not easy. So what do you think is the most common via on any circuit board? Anybody want to give me a guess? Ground. Right. The via to ground is your most common via. And so one of the first things to do is, how many vias to ground can I make the laser drilled one instead of the mechanical one? Which means that second question, what's the second most common via on a PC board? Is the via to power. So if you focus on ground and power, how can I make all of those connections microvias and not holes? You're going to go a big way in freeing up a lot of space. Well, they use the microvia in place of the through hole as a card. And look at layer stack-up changes to eliminate the drilled holes. So one of the things, you do not want to have a stack-up like you have in multi-layers. For one thing, typically you will have surface mount on layer 1 and a ground plane on layer 2 and a signal on layer 3, let's say. You now have enough room to eliminate layer 2. So you merge layer 2 ground with layer 1. You move ground up to the surface. Well, now I don't need a via to connect to ground. And you take power that's in the middle of the board and you move that up to layer 2. So that connection is a low inductance blind via. And layer 3 is the starting of the signal. So one of the easiest way to get rid of the big via is change your stack up. And so, depending if you have type 1, type 2, or type 3, figure out how to bring that ground plane from layer 2 up to layer 1. Now, not only does that eliminate a via, but it eliminates the EMI problems of radiation. Because now you have the opportunity to create a Faraday cage to trap it. I'll show you actual waveforms and emission charts that validates that. And so, these are all different methodologies, and they use skip vias or the the use of drilled ones, or simply multiple buildup layers, the type 3, which is multiple buildup layers. But just making the stack up differences. Yeah?
If you do this, do you then eliminate all traces on the top layers? Because else you would have a ground plane.
Right. Well, and so the one thing is, remember how close on the breakout the via was to the SMT LAN? Well, that, like on the type 2 there, that could be a skip via down to layer 3. So, you know, in my last example on the Vertec 5, all the single-ended were in layer 3, and all the differential pairs were in layer 5. And so there were no surface trading. So one of the things I don't like is routing on the surface. For one thing, it's difficult to control the transmission line because of the etching. But the other thing is that, and believe me when I tell you, if you move layer 2 to layer 1, you will gain 20 to 25% more return path. Now, the engineers violently disagree with me until I take their artwork and I bring it up and say, all right, let's measure the amount of copper on layer 2. Okay, let's merge it into layer 1 and measure the amount of copper. The amount of copper increased by 25%. And they said, how is that possible? I said, because fine pitch surface mount parts, even with a keep out, is smaller than a mechanically drilled anti-pad for layer 2. And so, especially electrical engineers don't have any concept of what a multilayer looks like on the inside. And they don't realize that by bringing that ground plane to the surface, they have a lower noise, better return path than when it's at layer 2. And believe me, I have endless fights about this for the last 40 years to convince electrical engineer that they're wrong, because they don't know what an anti-pad is. And an anti-pad is the opening we have to make in the reference planes to make sure we don't short that drilled through hole. So they have no concept of geometries involved here. But I can show them, and they walk away kind of with the tail between their legs, because I proved it. Look, you gain 32% more return path. This is by having that ground plane on the surface. And they're still scratching their heads, you know. Nobody's ever told me that before. I said, yes, they don't teach it in school, but that's the truth. And you can look at it yourself. You saw it on the screen. We measured the amount of copper. And that's because a lot of the features of a printed circuit board are hidden. And we did it this way 40 years ago. And they still want to do it this way now. Well, if you're in electronics, nothing in electronics today is like it was 40 years ago. So why should our circuit boards be the same? Nothing else in electronics. In semiconductor, if it's 10 years old, it's already out of fashion. But in printed circuits, we never get rid of the old stuff. We're still doing stuff we did 60 years ago. And I can't believe you're still doing things that were done 60 years ago. You know, we didn't even have ICs 60 years ago, and you guys are still doing it the same old way. There's much more modern techniques. Unfortunately, there are no books and no classes, and nobody's teaching you the modern techniques. They're still teaching you the 60, 80-year-old methodologies because there are no textbooks. And so at Michigan Tech, we have a printed circuit design course. Our textbook is the Printed Circuit Handbook, published in 2016. So it's only 3 years old. But we actually had to use the 7th edition of the Printed Circuit Handbook in order to have a textbook to teach modern printed circuit design, because there is no other. But other people, they're still using a 20 and 30-year-old printed circuit handbook. Well, a 20 and 30-year-old printed circuit handbook is the dark ages in electronics design compared to the semiconductors we have today. The rules in the fields keep changing. And so moving power and ground closer to the surface lowers the power distribution network's inductance. So one of the big problems we have today with the shrinking voltage is the power distribution, the PDN. We have to have very low impedance on that power distribution network in order to handle the high current switching that's going on. So we do that by what I call distributed capacitance. You move power and ground closer. I'll show you this afternoon the benefits of moving your power and ground as close as you can possibly get them in order to have coupling between power and ground to reduce noise. So this is one reason why you have your LAN pattern on the surface and your ground. Forget about any traces on the surface. Put the traces down inside the board. And put the power, and also why you can now use multiple split power planes. And I'll show you later here that they no longer become planes. They become coplanar RF distribution networks. And so a lot of people tell you there are 7 buried capacitance materials. Well, they're only telling you part of the truth. There are 7 expensive buried capacitance. There are 37 distributed capacitance materials. So one of the problems is that nobody will tell you the truth about materials. They'll only tell you about the expensive materials that they make a lot of money. They won't tell you about the cheap materials that work just as well. And so what I recommend in power and ground is the €1 3 mil core, which is, what is that? That's how many millimeters is 3 mils? 75 micron. Yeah, 75 micron. I recommend all of your power ground distribution be the 75 micron, because that is the cheapest core you can buy. Anything thinner than that, the price goes up exponentially and is not very effective until it gets down into the 10 micron core. And then the 10 micron cores that have very high dielectric constants have some enormous advantages for high frequency. But here's a list of typical materials and films and prepregs that are usable. And so I give the nanofarads per square inch and the picofarads per square centimeter of these materials. So all of these are suitable to provide distributed capacitance for high frequency noise. There's not just 7, there are 37 out there. So this next one is, this was supposed to be the power ground simulation. Since Altium doesn't have signal integrity tools, they asked me to take that out because that only makes headaches for them, for me to tell you how to use signal integrity simulation when they don't sell signal integrity. So it's in the handbooks, but it's not in my speech here because it's politically incorrect for me to talk about things that Altium can't do that you all know about because you're paying the price of not having signal integrity tools, but you've figured out how to get around that, I'm sure. Instead of what I want to talk about is vertical conductive structures. So this is an invention here in Europe to have HDI geometry without using a laser. So it's invented by a Danish guy over here, Jean Tormé. Really neat, but it's called vertically conductive structures. So this month in October, we're running a 6th article by Jean Tormé in PCB 007 about design tools and using this structure. So this is much, like I said, HDI is 40 years old. This is only 3 years old. But this is lower cost and high density. So I threw that in there because this is gaining more and more momentum in North America because of the low-cost nature and the high reliability. But the vertical one is that we create a slot in the PC board, and when we plate the slot and then drill it out, we use the vertical wall to connect to our inner layers rather than a hole. So a hole will handle 1 net. VECS will handle 12 nets. So in the space of the old technology for one net, we can now do 12 separate nets in the same space. So you can imagine how much greater this is in versatility for design, this VECS. And so this is one thing to take back. But remember, there are 6 articles on this in our magazine, so you need to go back a year and a half, collect all 6 in order to have because there are no books, and you won't find it anyplace else but in our magazine. If you contact Jean Tormé, he'll probably be glad to come out, this guy right here, and visit your company, because he lives in Denmark. And his company is called NextGen Technology, N-E-X-T-G-I-N, NextGen Technology. And you can see in the illustration how by drilling a number of holes or a slot, we can use these vertical walls for separate independent electrical nets. So I think it's great. I didn't invent it, but I think it's a great invention. And they come in blind and buried via fashions. And here are cross sections. And look at this right here. This is his illustration, because it says right there, VECS technology and Altium design system. He actually uses an Altium design system, but Altium doesn't know anything about this, and you have to fight Altium to do this. So all of you, if you like this VECS, beat on Altium to make a VECS drop-down menu so that you can click on it, and it gives you the right artwork. Because right now you have to fool Altium to get the right artwork. But Altium, with no changes at all, could do a rev to have you a VCS drop down. And then you could all take advantage of high density without any increase in cost. But it takes your concerted effort to demand it from Altium if you want that change. And it's a simple change. But the way it works is you drill or route holes or slot to create a slot in the board. You metallize that slot. You image separate nets up to the slot. You electroplate up the copper. You strip, etch it. And then in final fabrication, you mechanically drill out the copper that shorts them all together. So, this becomes 6 separate nets. You can see up there, you have 6 separate nets using the same geometric area. Now, this could be done with a big hole. And we come into the hole from forward sides, vector, and then we cut it out. So in addition to being a slot, it could just be a hole. But now the via hole, instead of having one net, the via hole will handle 2, 3, or 4 separate electrical nets. Big savings in space, but also big improvement in signal integrity. The kind of an isometric view. Here's the comparison of through hole in terms of routing at 1 millimeter pitch and 0.5 millimeter pitch, and HDI, which is the microvia, and the VECS. And you can see that the VCS at 1 millimeter pitch has the same separate tracks as microvias. At 0.5, it can get only 5 tracks, but the microvia can get 7 tracks. So it's not exactly as high density as HDI, but it's enormously lower in cost because the fabricator doesn't have to buy the very expensive laser and doesn't have to deal with the problems of plating a blind via, which is very difficult. So it's much lower in cost when you actually buy the PC board. But again, it's not a multi-layer. It's a whole different strategy in terms of how you do your wiring. The 5th one is, if possible, create 2 adjacent microstrip signal layers that are part of the microvia or VECS structure. So you have a horizontal and vertical, so that we can go horizontal and vertical routing without using the big through hole. If you can do your X and Y on that top 2 or 3 layers, you're going to get 8 to 10 times more routing than the center of the board. And so always recommend that your most sensitive electrical nets are routed closest to that surface ground flood for coupling. And that because there's so much higher density, by the time you get most of that routing done, the rest of the non-critical routing can be done as a conventional multilayer in the center cores, as well as the rest of the power distribution. So it's not just me. One of my companies I consulted with, this is Cisco. This is actually a copy of a Cisco PC board. And you can see up here that I've circled how Cisco has specifically adopted a horizontal vertical two-layer routing strategies here and here. And those will always be their most sensitive nets, will be that. And then these nets right here, much, much less sensitivity because they're influenced by these through holes. These two nets up here, they don't let a through hole anywhere near any of the sensitive traces because of noise coupling. So if you don't believe me, believe Cisco. They gave me permission to use one of their telecom boards as an example of taking HDI technology and using it in a proper fashion. The number 6 one, and that's right now, well, these are all English units, but 4 and 4 to 3 and 3 to 2 and 3 is we're going down in geometries. Right now, a lot of PC boards are routed at 50 micron lines and spaces or 60 micron lines and spaces. Some of the newer designs, the iPhone 5, the iPhone 10 and iPhone 11 are 25 micron lines and spaces. So if you got an iPhone, the iPhone 10 was 30 micron lines and spaces. And so if you're still using 100 micron lines and spaces or 125 micron, my question is why? Why are you still, everything is getting smaller. Even with transmission lines, if you go to a 50 micron line in space, then you go to very thin material, and the whole thing weighs less and is smaller. But not just the traces and spaces, but the buildup layers and the lands and the holes. There needs to be a roadmap where everything's getting smaller and smaller and smaller. And you should demand from whoever builds your product, do they have a roadmap? What can I use next year? What can I use the year after in terms of you're improving the performance to match what the semiconductor guys are doing to us, to their demands? And one of the things, we're making everything smaller. And so we're moving our vias closer together or eliminating the vias to reduce inductance because we've got all these current loops and we want to minimize the dt of the current changes in order to reduce noise. And so by making everything thinner and closer and smaller, we reduce that inductance loop that's there. All the way point to the landless via is now practical. So I've been using these things since 1984. And our Japanese partner started showing us their PC boards that had no lands on them. And we said, well, that won't work. And the Japanese just smiled at us and they said, well, test it. So, okay, we went out and we tested it. And lo and behold, the Japanese were right. The landless via right there was 10 times more reliable than a via that had a pad on it. And so we were just scratching our heads. Well, gee, for one thing, the IPC says you're not allowed to do this. Well, guess what? The IPC is wrong. The US military is wrong. They never bothered to test it. They just thought that this is bad. We had the actual test data, and in fact, this is 10 times more reliable than the vias you guys are using. And it's a hell of a lot cheaper because notice right here, without a land, you can put those traces close together. In fact, and so a bunch of 4 PhDs from HP Laboratories, who are really smart men, went back and they created the model to explain why the landless vias are 10 times more reliable. And the paper is available from some of my publications. Yeah. Oh, okay. That's next slide. Oh, so the other thing is people say it's impossible to do. And I said, well, this is a test. Ask your fabricator about landless. And if he says it's impossible, turn around, walk away, and find another fabricator. Because you want a fabricator that answers the question by saying, I've never done that before, but I'll give it a try. If he says it's impossible, leave as fast as you can. You do not want to buy from that guy. He's dumb. But if the guy says, I'll give it a try, that's somebody worth working with. So guess what? There are 4 ways to do it that cost no money at all. And you want the guy that figures out one of those 4 ways. Now, the quickest way is to read my magazine and books, because I tell you how to do it. But in 1986, we had to figure it out. And so, the first way is the Japanese way that our partner introduced to us. That works in North America, but it's different because that uses what we call a liquid electrophoretic positive photoresist. Anybody ever heard of that? No, you got. And so if you show that one out, they all look at you. Well, guess what? It's a semiconductor photoresist used. So it's good down to about 12 micron geometry. So 12 micron, yeah, okay. It's electrophoretic. What does that mean? That means as a liquid, you electroplate it onto the board. It's an offshoot of electrophoretic automotive paint, where they ground the auto body, dip it in, and they charge the paint, and the paint covers it uniformly. Well, this is the same thing, but it's a photoresist, not a paint. And it's positive acting. I won't go into the explanation of why positive acting is better, but for the last 50 years, we've only made semiconductors with positive photoresist. Printed circuit people use negative. The IC guy gave up negative photoresist 50 years ago because it's not very good. In printed circuits, we continue to use negative, but we should be using positive. I won't go into you about how dumb printed circuit fabricators are, but they're using a 60-year-old technology. And if they went to their semiconductor brothers, they found out they should be using positive. And, the second way is the way we did it in Hewlett-Packard. Okay, we didn't want to change the mechanical process, so we came up with a solution out of the box that doesn't cost a cent and allows us to make things. The third way is the Russian way, and guess what? Unfortunately, the Russians have been using this for 40 years on their military stuff, which is sad because I wish I had thought up the Russian way, but I didn't invent that way. And then the fourth way, what happened to my, I don't know why the bottom popped up there. Well, the fourth way is with new equipment. And well, so if you go to that machine right there, that is a direct imaging exposure unit. It has 9 cameras. So as the printed circuit board goes into the machine, the 9 cameras measures every hole on the top and on the bottom. And in milliseconds, it morphs your artwork so that every pad is perfectly aligned as it's exposed and comes out of the machine. Because it's DLP mirrors from Texas Instrument, and the software is so fast that this machine produces perfect registration. So if you choose to have a landless via, every single land is perfectly aligned no matter where the hole is. So it doesn't use a program for the holes. It measures the actual drilled hole and then morphs the artwork to perfectly match it. And so this gives you landless vias But it also gives you a great turnaround time because Wednesday evening, if you're still here, I'll talk about the smart factory. This is an exposure unit for the smart factory that's driven totally by software. So it produces 4-micron lines and spaces and 20-micron holes with 99.7% yield that it cannot be built in Europe or anywhere in the world. But the Americans now have this factory that can make semiconductor geometries as printed circuit boards. But I'll talk about that next generation smart factory Wednesday night. And they don't use this machine. They use a Swiss machine that's better than this one. But this is an American machine. They actually use a better one, which is made in Switzerland for the semiconductor people. But this is the explanation of why landless vias are 10 times more reliable that you can get the technical paper for. So this is 1986 from the Japanese. So this is the electrophoretic resist used in North America. This is what I call an invisible via. The 100-micron traces have 100-micron vias in them. So you notice what an advantage that is to have all these bus structures and be able to go in the next route a different direction and not have a LAN that spreads everything out like right here. Yeah. So there's an enormous advantage of having this landless via technology when it comes to design. And so you have to push back and find the fabricators that'll manufacture this so you can take advantage of this. Because guess what? We've been doing this for 40 years in North America, and so is the Japanese. You guys are 40 years behind us in certain architectures of design because we keep this stuff secret. We don't let you know that we're doing this. And we don't tell the IPC or anybody else. But you know, time that these secrets be let out of the bag, that there's better ways of doing things than what you may have seen. Number 7, removal of decoupling capacitors. So I talked about distributed capacitance. When you're in high frequency, there is so much inductance associated with a chip capacitor that no surface mount capacitor can ever handle the high frequency noise. There's just too much serial inductance. You actually have to have power ground layers close together in order to shunt that noise. And so these are the distributed capacitance materials. And the best is the most expensive, the 3M at the top, and it goes down. What that does is it looks like this. You know, these are capacitors, but this right here is power ground pair. And the only way you're going to handle the lower inductance at the higher frequency is power ground pair. I don't know how many of you use power ground pair, but you're going to get used to using it more and more and more with the newer chips because of the reduced noise budget and the shunting of high frequency noise with that. And so one of the things that I've done is I've taken this 16-layer through hole and made it into a 12-layer HDI board, but I've also built this in 4 different HDI technologies down to a 6-layer. So this afternoon we'll talk about 2nd and 3rd generation HDI. Right now I've been talking about 1st generation HDI, which is 40 years old. This afternoon I'll talk about 20-year-old HDI and 10-year-old HDI, none of which you do here in Europe, but the Asians do it. And why those 2nd and 3rd generations are better than what you're doing now and even what we're doing in North America, because we're already into a 3rd generation HDI. And a lot of you are just adopting the 1st generation. So you've got to remember, you're adopting something that's 40 years old. So you may choose to adopt 3rd generation and skip over. And so stop doing what you're doing now and jump to 3rd generation. Because 3rd generation is green materials that are recyclable. And have a whole bunch of other benefits that the 1st and 2nd generation doesn't have. And so to do this, we actually had a hands-on 3-day course for HDI technology in North America, sponsored by the Department of Defense. So Crane, what we call Crane up there, that's our largest US naval base. and it's 2,000 kilometers from the ocean. So our biggest naval base is 2,000 kilometers from the ocean. They created it in World War II to be as far from the ocean as possible. So it's in the center of the United States. Is one of the world's biggest Navy bases in the center of the United States. But they have a state-of-the-art printed circuit facility. They also have linear accelerators to simulate nuclear explosions. So when they work with electronics, they can put their electronics out and submit it to a hydrogen blast through this linear accelerator, so that their electronics isn't burned up by electromotive pulses of a nuclear explosion. It's a fascinating place. But anyway, the military let us use their PC shop, and they let us do a training course as open to everybody as long as they're a member of NATO or CETO. If you weren't a member of NATO or CETO, you can't come to the course because the course is actually at the PC shop on the Navy base, and you have to go through all the military to get there. Unfortunately, when we advertised this is for North America, the people from Turkey jumped in and took all the seats. We didn't. We had to throw half of the Turks out to make room for some Canadian and British and American. But we're kind of flabbergasted that 60 applications came in from Turkey. And they took all the seats, and we had to take the seats away from them because, well, wait a minute. Essentially, this is for North America. We don't mind for the Americans and the Canadians, we don't mind the English and the French or the Germans, but where the hell did all you Turks come from and why? It's like, we're not very visible what's happening in Turkey, in terms of military products. But it was interesting meeting these guys from Turkey and all the military programs they're working on, because to us, they're kind of like invisible. We know what Israel is doing, but don't know anything about what Turkey is doing. But they are a member of NATO, so they qualified. They just found it very interesting that the Americans would let all these foreigners onto a high-security military base. Hey, I don't make the rules. But there was a lot of areas blocked off where they're doing live round testing and artillery. Do not go down this road. Do not go down this road. They're testing live ammunition down there. Because we're constantly being bombarded with noise in the background. It's a huge 55,000 people work there. Comes from 8 different states into this every day and then go home at night. This thing is enormous. And why do they have a PCB shop? Because this PC shop will build, if you send them electronics from an aircraft, a ship, or a tank, and it's 30 years old, they will rebuild the entire PC board, reverse engineer it, build the board, assemble it, test it, and send it back to the fleet or send it back to the aircraft. Doesn't matter how old it is, their job is to replace operational military electronics, no matter how old it is. And they're remarkable in what they can build for whatever is out there. Because they store all the wafers for all the North American military products. So they have these ammunition bunkers. They're filled with wafers in nitrogen. They're not filled with ammunition. They're filled with silicon wafers of 20-year-old, 30-year-old, 10-year-old military products. And the entire wafer is stored there. And they'll go there, grab the wafer, dice it, take it off, test it, package it, design the PC board, put it on the PC board, test it, and then send it back to whoever has. Except 3 weeks out of the year, all the doors are closed, it's locked down, and they build multiple reentry vehicle Trident missile controls units. So for 3 weeks out of the year, they build all the Trident nuclear warhead MIRVs, electronics. And the reason is the plutonium MIRVs burn out all the electronics after about 2 or 3 years. So after 2 or 3 years, you have to replace electronic on these multiple reentry vehicles because the plutonium flux density burns out the silicon and stuff. So, they're constantly making new warhead PC boards, and that is highly sensitive. So everything is locked down where they manufacture. But other than those 3 weeks, they don't know day to day what they're going to be working on, just whatever comes in. And that's Crane. And they let us use it for free. So we got to use a state-of-the-art facility with engineers and chemistry for training, of commercial people. So here's the power distribution network impedance. In this particular one, we have to have a power network less than 0.1 ohms. So our goal here is to have 0.1 ohm power impedance. And you can see the original design is in blue, and here's 0.1 ohms. The yellow design right there is the HDI. This is the 3.3 volt. So we put this thing together, and the first thing we found is that you don't want decoupling capacitors. Notice the original design, it has 100.01s. The final HD design only has 12. It had 60.1s, the final has 14, and we still have the 1200 microfarad. So guess what? Distributed capacitance is great, but if you're going to use it, you got to take away the decoupling caps, because the decoupling caps kills the technology because it forms resonant circuits, and you get all kinds of peaks. And so we kept taking away the decoupling caps until the thing finally worked. We also found that the decoupling caps don't have to be near critical. They just have to be in a matrix. So you put them in non-critical areas in a matrix. You don't have to put them next to critical devices. So the same thing was true for the 2.5 volt. The original design is in blue. The finished design is in yellow. And we had to take away 28.01s. We had to take away 40.1s and still had the 110 microfarad. So the good news is distributed capacitance is really great, but it also means that you can take away 80% of the decoupling caps you can throw away. You don't have to buy them, design them in. You need 10 to 20%, but that's the last thing you can place on the board because they don't have to be in critical locations. They just kind of have to be in a matrix. So it's really interesting that the removal of decoupling caps gives you higher performance and more space that you need. And interesting enough, the savings of the decoupling caps actually pays for the more expensive material. And then the last one is use of split power and ground planes. So, you're used to a single ground plane. Some of you probably use a split rail. How many use split planes? That's pretty common. Okay, so you got 2 different voltages on the same plane. Well, how many do I use? I use 12 to 14 voltage rails on the same plane. And that's C up there. Why? Because it's what we call a mesh. We have a power mesh, and each power grid is a different voltage rail. And so we have to have 2 layers, one in the X and one in the Y. And wherever the cross, we put a via there. And so by creating this mesh, this is exactly the way we do an IC design, we have no IR drops. And so instead of a plane, we have designed in a non-impedance drop source of power. But the advantage is up there is that in between the mesh, we can put our signals. And so in RF, this is called an offset coplanar strip line, which is an RF structure. So you notice that power and ground is coplanar. Ground is on the surface, but power is coplanar. And you can do this with the polar systems, but this is a better high-frequency architecture for 5G and 4G telecommunications for very high speed because of the magnetic fields. There's less fringing involved. But the other beauty is, like here, is that, that whatever you're doing now in 12 and 14 layers, with Power Mesh, I can do as a 4-layer board. So would you rather buy your 14 and 16 layer or my 4-layer, when my 4-layer costs a third of what yours costs and has higher level performance with less noise? So you can do it your way, you can do it my way, but I'm going to win the business in the long run because I have better performance and simpler designs. And it's what we call power mesh, but this is the way we design an IC because we don't have power and ground planes in our integrated circuits. We have a mesh structure, and it works great on circuit boards. In fact, it works fantastic on circuit boards. And so here are some of the impedances for your 50 and 100 ohms differential. You know, what are the geometries involved? Well, these are all straight out of Polar. I mean, you know, nothing fancy about this. And if you have an RF friend who's in RF design, they'll tell you this is 50, 60 years old. This is not new to them. It is new to the digital field. But we're at such frequencies now in our bits per second that we're in the RF signal area, even though we're digital. And so this is actually examples of power mesh boards. These boards right here, these are 4-layer. Their through-hole equivalent were 12 layers. So these were taken from 12 layers to 4 layers. Let's see, oh, this is not HP. HP did this for Motorola. This one is HP. This went to from 12 layers to 4 layers. This one went from 12 layers to 4 layers as well. And this one Hewlett-Packard did for Texas Instrument. Texas Instrument wanted the notebook computer to have only the components on one side. So we took this from a 10-layer to a 4-layer with everything on one side. So TI was flabbergasted that the best they could do was a 10-layer with parts on both sides, but at Hewlett-Packard, we did it as a 4-layer, everything on one side. And so we had to spend a lot of time teaching TI, how is this possible? Nobody else is talking about this architecture. How can you guys in Hewlett-Packard do this? We've never heard this, read this. We said, well, it's a secret. We're not going to patent it. It's just a secret. We just know a lot more about board design than you do because nobody's teaching board design. You know, we're actually doing research on board design. That's how we came up with Power Mesh. Power Mesh was my idea because of my IC designers telling me, why am I still doing it this way? In ICs, we do it this way. And I said, boy, oh, that sounds like a better way to do it. How come nobody in printed circuit does it that way? But my boss said, hey, if the IC does it, we give it a try. Let's make some test vehicles. Let's not argue about it. Let's build it and test it and see what the data says. And the data came back spectacular, kind of like the landless vias. So they said, okay, let's not tell everybody else about this. Let's not publish any papers. Let's not patent it. Let's just make it our little secret. Oh, this one right here, that's Intel. So Intel was flabbergasted that we took their 12-layer and made it into a 4-layer. So as smart as Intel was, you know, they threw money at us to teach them, how did you do that? Because we've never seen a design like this. And so, okay, Intel, we'll teach you how we designed the board. Because when they populated it, this was so much better than their design electrically. And they claim they have the best in the world. So how could we be so much better if they have the best? They were kind of scratching their heads. They said, well, you don't have HP laboratories sitting over here on the side, which is like Bell Labs. It's filled with really smart people. So, you know, we didn't necessarily invent this. We had the guys in the labs kind of invent it and tell us, but it's still, you know, our knowledge and not general knowledge. And so one of the things that humored me is, if I used any IPC standard, I'd get fired. IPC standards were so reviled by Hewlett-Packard that they were considered propaganda. And one thing I learned very early, never mention an IP standard in Hewlett-Packard, I could end up being fired, because to Hewlett-Packard, the IPC was promoting propaganda. They had no data to support it, old white men voting on things. And so Hewlett-Packard, like IBM, had their own standards. And 80% of them violated every IPC rule because the IPC stuff was pure propaganda. I mean, I work a lot with the IPC, but what I'm trying to do is getting rid of the propaganda and replacing it with facts. And that's why the IPC is testing the landless vias, because I provided enough data to show that they've been screwing everybody for 40 years with their insistence that a via have a LAN, when we have data that shows that that only makes them unreliable. And when it goes back to the validating by the military that worked with us, they can only say, oh, maybe you're right, we better rethink our standards, because everybody in the world has fistfights over IPC standards, and they're all wrong, because there's no data to back them up. Unfortunately, it's the only standards out there. So a bad standard is, I guess, better than no standard. But a bad standard can lead you in the kind of the wrong direction. With that, we go on to the next one before lunch.